Welcome back. So we have been looking at how to use graph theory to model various problems. Now, modeling problems in mathematical languages is in general a very powerful tool. In this set of 3 videos, we will be focusing on that particular aspect of problem solving, namely how one can model different problems into other mathematical languages. So, first of all, one way of attacking problems is modeling the problem in other mathematical languages. We have done so even in our high school when we used to use polynomials or factorization of polynomials, quadratic equations and so on to solve the equations, or even when we used general technique of solving linear equations to solve various problems. In our high school we saw how to use calculus for obtaining the maximum and minimum of various functions. Similarly, we saw in the last few videos how to use graph theory to model various problems. Now the main use of this using modeling problems in different mathematical language is that you can then use the powerful tools that are developed in various other mathematical subjects for solving your problem. Now there are various different mathematical languages that one can use to model one problem. Depending on the problem, what is the right language to represent or model the problem can be asked. Till now we have looked at graph theory. In this video I will be looking at something called linear programming, another very powerful mathematical model using which we can model various discrete problems. As I told you, it is you should not think that these are the only 2 ways of representing problems. There are a zillions of other ways of representing problems, but graph theory and linear programming are the most commonly used technique of representing problems. Right? So while graph theory we saw is mostly used to represent binary relation, the linear programming is used to solve optimization problems. Now, what do we mean by optimization problem? It means that we want to maximize or minimize something, say for example cost of something or profit of something and so on, under certain conditions being satisfied. So here are a couple of examples from the industry world which is used, in which optimization is used a lot. In this video we will be looking at some problems, from naturally occurring problems in industry which are optimization problems, and we will see how to use LP, linear programming, or in general mathematical languages to model these problems. So here is the first problem. Say in the first problem, a trading company is trying to maximize profit per transportation of goods. This trading company has 3 wagons available. Now, when stocking the wagon, they can use 4 types of good, right? So here there are the 4 different cargoes, C1 to CR, C4, and here are their wagons, right? Now, each wagon has a weight capacity and a space capacity, and each cargo has a volume per ton, how much is there, And if you manage to ship that much amount of thing, what is the profit that is there? Now this is a typical problem that a shipping industry faces all the time. So it has 3 ships. Each ship has some weight capacity, some space capacity. Now there are various kind of cargoes, C1 to C4. Each of them has a certain amount of available quantity, and each of them takes certain amount of volume, and each of them has certain amount of profit involved in it. Now how can you pack these quantities into different wagons so that you would optimize or maximize the amount of profit? Right? So there are various heuristic problems that one can come up with. So maybe the cargo that has the maximum profit per weight, let's take that one. But maybe if we take some object which has the maximum profit per weight, namely say this one, C3, then I can only fill up only 5 tons, and total volume available is just pretty low. Whereas if I take the next one, say, is it better to take the C4 or is it better to take C3? Although C4 will get more profit per ton, C4 also takes up a lot more volume. Whereas while for C2 I have slightly less amount of profit, but I can pack more objects in it, in the ship or in the wagon. Right? So this is a typical problem that is faced all the time in the wagon industry. If you are a bit more, if you want to think of it slightly easily, think of just one wagon. You have just one wagon with the capacity, weight capacity and the space capacity. That means the capacity, weight capacity meaning you cannot exceed the weight. So how much amount of quantity can you store in wagon 1? It is 10 tons. And how much space can you use in that wagon? It is say 5,000 liters. Similarly, in wagon 2, you can at the most pack 8 tons, and space capacity is 4,000 liters. And wagon 3, you have weight capacity of 12 tons and space capacity of only 8,000 tons, 8,000 liters. And the cargoes have different. So of course, the goal will be to maximize profit such that none of the wagons are overloaded, either in terms of weight or in terms of space. Now question is that how much do you fill in each of the wagons and what cargo do you fill? So we will be looking at this problem, and there are 3 more problems. Let me first describe those 3 problems and I will go back to this problem after that. The next problem is another problem from the industry world, namely banned for buck in advertisement. So for example, say you have a marketing budget of 6 crores, right? And you can spend this money in various ways. Now you have only 10 people handling the whole advertisement part of your company. So one thing that you can do is that you can maybe invest 3.5 crore to create an advertisement for Cricket World Cup. In that case, you will be expecting to reach something like 10 crore people, but you will need 5 people to make sure that the advertisement works. Whereas you can have the IPL, maybe you will be reaching 15 crore people, the cost will be more, and also the number of people that you will be using or needing is 7 people. Similarly, for radio, the cost is very low, 0.1 crore, but you expect to reach half a crore people, and you also need only 3 people. And similarly, like this. Question is that how much or which of these things should you invest in? For example, if you decide to invest in Cricket World Cup, you have to spend 3.5 crore, and in which case you have to allocate 5 people for it. So if you, for example, I have only 10 people, what it means is that I cannot invest in both Cricket World Cup and IPL. Right? Or I cannot invest in both IPL and TV ads for non-peak times. Because IPL will require 7 people and TV ads will require 4 people. So all total I need 11 people, but I only have 10 people. At the end of the day, I also have only 6 crore. So I cannot invest, for example, in IPL and TV non-peak ads. Because IPL will require 5.2 crores and this will take 1.5 crores. So all total I will require more than 6 crores. So the goal at the end is to maximize the expected number of people you are reaching under the condition that you spend less than 6 crore and you all total the number of people required is less than what you have 10. So again, this is a typical problem in an optimization problem, where you trying to optimize the profit, or here in this case expected reach, under the condition of certain conditions, which is here upper bound of the budget and the number of people being used. Let me look at the third problem. The third problem is about telephone towers. You have n important locations in the city. Now you want to upgrade some of the infrastructure of some of the towers to some 3G connection or maybe 4G connection. Now, if a location is less than 1 kilometer from any tower that has improved location, then it will have good 3G connection. The company of course wants to minimize the number of towers it has to upgrade, so that at the end it also wants to ensure that everybody in the city or everybody in all these n important locations in the city has good telephone connection or get good 3G connection. Right? Again, it is an optimization problem, it's a minimization problem, where you want to minimize the number of telephone towers to be upgraded under the condition that every person or all the n important locations is less than 1 kilometer from any tower that is upgraded. For some tower that is upgraded. So again, this is an optimization problem, a problem that occurs in real time in the industry world quite often. The fourth problem is a problem that industry HRs have to decide. So they have to, when there is a meeting that has to be decided and they have to book hotel rooms for various meetings. So here is a list of meetings that will happen. There is meeting 1 that will start at 9 a.m. and end at 11 a.m. Meeting 2 that starts at 10 a.m. and end at 11 a.m. and so on. Now of course 2 meetings that clash in the same time, for example meeting 1 and meeting 2, cannot be held in the same room. So the HR has to decide what is the minimum number of rooms to book so that all the meetings are held peacefully. So we would need to solve this problem also. So here again it's an optimization problem. It's minimize the number of rooms required for solving all, for ensuring that all the meetings happen without any clash. So here are the four problems that I have picked up, and we will see how all these problems can be written in the language of linear programming and graph theory, and that is how one would like to model these various real life problems. Now, most of these problems, or at least a few of them, have some common properties in them. Common approach is what is called a linear programming. Now, what is linear programming? So, linear programming is the simplest form of optimization problem that you can think of, where we want to optimize, say in this example, we have to maximize some equation. So, for example, here 3x plus 4y minus 10z, where some equations are satisfied. For example, under this set of equations. So I have been given this set of equations: 5x plus 8y is less than 15, x plus 5y plus 2z is less than or equal to 10, and so on and so forth. And of course we have been told that okay, x and y are numbers between 0 and 1, z is a positive number, and under such conditions, what is the maximum that we can have? Now this is a typical form of linear programming. Linear because all the constraints as well as the optimizing function are linear, meaning they are degree 1 polynomial. Okay, so then we don't have something like x square or xy in the coefficients. So I have the 3x plus 4y minus 10z. Right? So it's a linear term. Now, again, one thing to note is that when we add this condition that x, y, z are real numbers and not just integers, they are from the real numbers, then this is called the linear programming. We will be talking about the case when they are not real numbers, possibly the next video. But in this video, let's assume that x, y, z are real numbers. And in that case, this structure or this whole thing is called a linear programming. Now, the usefulness of linear programming is that linear programming can be solved pretty quickly, and there are well-known structure on that. In fact, in R, one of the very useful machine languages tools that is there is a package that can solve it straight. So if you have such a thing, you can feed the program in a particular way, and in which case you get the linear program solution. So if I can convert those problems into an instance of linear program, then I can use the concepts of linear programming to solve the problem. So linear programming is a very well studied subject, and there are lots of different algorithms are known. When the variables are allowed to be real numbers, then we can solve it very quickly. There are some nice packages in various languages that can help it to solve. The trick is modeling the problems in the linear programming form. So let's start with the first problem. You remember? So just for the sake of simplicity, I have reduced down the number of wagons to 2 and the number of cargoes to 3. Now how do you solve it? Say I start with saying that we have these 3 cargoes and 2 wagons. Let's say that x1 is the amount of cargo 1 in wagon 1. y1 is the amount of cargo 1 in wagon 2. Similarly, x2 is the amount of cargo 2 in wagon 1, and Y2 is the amount of cargo 2 in wagon 2, and similarly for X3 and Y3. So now that this has done, we can now quickly calculate first of all how much profit we have and also what are the restrictions, right? So what is the thing that we maximize? We maximize the profit. Now if X1 and X2, if I manage to ship X1 plus Y1 amount, X1 in wagon 1 and Y1 in wagon 2, so the profit that we have is 2000 times X1 plus Y1. Similarly, for cargo 2, it is 2500 times X2 plus Y2 and 5000 times X3 plus Y3 for cargo 3. And what are the conditions? Let's look at it. There is the weight conditions, right? So weight condition says that the wagon 1 cannot take more than 10 kgs. Or which, okay, sorry, not this one. The weight conditions are that there are only, in cargo 1, only 18 tons are available. So X1 plus Y1 is less than 18. Similarly, only 10 tons are available for cargo 2. So X2 plus Y2 is less than 10, and similarly X3 plus Y3 is less than 5. So this is one of the condition. Some more condition. The other condition is the capacity of the wagon. The amount of weight that is going in wagon 1 must be less than 10. Namely, that X1 plus X2 plus X3 must be less than 10. And similarly for the wagon 2, Y1 plus Y2 plus Y3 must be less than or equal to 8. And the third one is the space capacity. Now what is the space capacity? How much space do we end up spending? So if 400 is the amount of for the volume per ton for the cargo 1 is 400, the amount of volume required for shipping X1 amount in wagon 1 is 400 X1, right? Similarly, amount of volume required for shipping amount X2 of cargo 2 is 300 X2 and so on. So we get 400 X1 plus 300 X2 plus 200 X3. This should be 5000 is an upper bound on the volume that can be spent. So this is less than or equal to 500. And similarly this number for the case of wagon 2. So here is the question. We have got the set of inequalities, which are the conditions, and what we want to maximize. And we know that all of them must be greater than 0. X1, X2, X3 and Y1, Y2, Y3 must be greater than 0. Now this is typically in the form of a LP, and we can solve it. And once we solve it, using whatever programs LP solvers that we have, we get an optimum solution for this problem. Right? So here is an LP, you solve it and we get the optimum solution. Here of course we can assume that X1, X2, X3 and Y1, Y2, Y3 are from the real numbers. So this can be solved using LP solvers, and hence we have seen how we can reduce that problem or model this problem using LP and then use the standard tools that we have for LP solvers to solve this problem. Okay, in the next video we will be looking at the second problem and how one can use linear programming again to solve this problem. Thank you.